today. So as I mentioned in class, we're going to be looking at other potentials, ones that at least only have bound states. So they should go up towards infinity as you go off to plus or minus infinity. In other words, they're not going to allow any scattering states. And we're going to solve the time-independent Schrodinger equation. We're going to look for those bound states, those definite energy, stationary states, separable solutions, if you like, the position part of the separable solution. And so what I've got here is just rewriting the time-independent Schrodinger equation, H psi equals E psi. And, you know, to try to get going on a solution, let's solve for the second derivative. And we want to, in MATLAB, approximate that second derivative by finite differences. In other words, like d psi dx by a delta psi over delta x, and that will tell us how to step forward. We'll see how to do that. But maybe first, because this one involves a second derivative, and I don't know how much you guys know, if anything, about solving differential equations on computers, it might be simpler to think of a first order differential equation and just think about how we can use finite differences for that. So, you know, let's just make up a simpler differential equation for how psi changes with x, and I'm going to make it a first order one, you know, just something like d psi dx equals 2x. That would be, you know, like day one in differential equations or something like that. But we're going to produce numerical solutions to this. And, you know, in MATLAB, of course, there's no continuum x. We need to make a vector of x values. Hopefully this is something that at least sounds familiar, right? So if I imagine just drawing a picture of the x-axis here, I'm not going to have a continuum of x's, but rather I'm going to have a vector of x values that's of some length. Maybe I have nx values. Right, so I might say, you know, in MATLAB, I might say something like, I want my x vector. I might even call it x vec. Maybe I'll just call it x, I don't know. You could call it either one. And there's that command linspace that makes a bunch of equally spaced values of a certain length, right? So if I wanted, if I had some minimum value that I had decided on, that's going to be the first x value in the vector, and the maximum value, and the number of x values that I want, maybe 100, maybe 500, depends on how much resolution I want. Then, you know, inside of MATLAB, of course, I'm dividing up the x-axis into lots of little things, right? And I might say, here's what I'm going to call the first bin, and here's the second bin, and the, you know, the x values are at the center of those bins. Somewhere up here, you know, sort of in the middle, I might have the nth bin and the n plus first bin and the n minus 1th bin and so on. And then here is the last bin. It's got an index nx. And we might refer to the x values at the center of these bins as, you know, xn, xn plus 1, xn minus 1. Hopefully that's not news to you guys, right? So I'm sort of trying to translate into a model from MATLAB. That would be our representation of the x values. And if we want a function psi of x, what we do is have another vector of the same length. I might label it as psi, psi. And along the x direction, I'm also going to have a psi n. And, you know, the next one in this bin and in this bin, I'm going to have a psi index n plus 1. I'm going to have the same number of those, right? And that allows me to store a function, right? For each x, I've got an associated psi value. All right, so how am I going to solve this? Well, as I mentioned, at least in the first order case, we're going to use what's called Euler's method first, and we'll do a slight improvement on that. But I approximate this by finite differences, right? Approximate the derivative like that. And then what I want to know is if I'm at a particular position, if I know what psi is in position n, how do I go over and determine what psi is at the next position up, or maybe in the next position down? And that's given by solving for delta psi here. So just taking it one step at a time, delta psi is equal to 2x times delta x. And I could think of this if I already know the value of psi, say in position 1, or maybe more generically in position n, this is, the change in psi from one bin to the next would be like psi at position n plus 1 minus psi at position n. That's the change in psi. And that would be equal to 2 times x in position n times whatever delta x is. And, I could always define a variable in MATLAB, once I figured out what my x vec is, or maybe it's just easier to call it x. Remember, it's a vector. I could calculate what dx is. That's just x2 minus x1. Since they're all equally spaced, I could just calculate it once. I don't have to think about it. I know what my dx is. And so at least in terms of MATLAB kind of stuff, of course, I need multiplication signs and all that, but I'm kind of writing something that might work in MATLAB except for the multiplication signs. And so this means now, if I know what psi n is, I can get psi in the next position. Psi in position n plus 2x in position n times dx. And of course, in MATLAB, I need multiplication symbols in there. Got to put the little star in there to multiply. Okay, so that's telling me if I know psi in position 1, I can calculate psi in position 2, and so on, and so on, and so on, and so on. That's called Euler's method. Just means you're replacing an ordinary derivative with finite differences in the numerator and denominator. So that would allow me to move to the right. If you know some initial condition, what is psi at some position, I can go forward, and then I can go forward from there, and so on, and so on, and so on, and so on, right? I can get the n plus 2 position in terms of the n plus 1 position, and so on. I can also go backwards. I could have, if I think of this next one over here as psi in position n minus 1, another way to calculate delta psi is psi in position n minus psi in position n minus 1. That's a perfectly valid delta psi, right? I'm just doing the later one minus the earlier one. I just chose a different index there, right? And I could say, well, that's equal to the same thing. That's equal to 2x times delta x. And therefore, I could solve for psi at n minus 1. That means if I know where I am here, I can also solve the differential equation to the left. I can sort of step in the negative direction. All right, so that would be psi in position n minus 1 is equal to psi in position n minus 2 times x in position n times dx. Need my multiplication symbols, of course. So what these are telling me is if I've got a differential equation and I know some value in the middle, I can solve it to the right and I can solve it to the left. Once I've got a position, I can get the next one, then I can get the next one, and so on and so on and so on. Okay, and I can write a for loop to do that for me. Now here we've got a little bit more of an issue because, well, wait a minute, how do I do that with a second derivative here? And the answer is, usually when you're doing things in a computer, you write a second order differential equation as a system of 2 first order differential equations in the following manner. I define d psi dx to be some new symbol psi prime. Okay, in my variable in here, I'm going to call it psip, psi prime. Okay, so d psi dx by definition is something I'm going to call psi prime. And then our differential equation tells us about d psi prime dx. That would be psi double prime, or d squared psi dx squared. Right, so this system of differential equations, by defining a new symbol psi prime, gives me something that's completely equivalent to that second order differential equation. But now I can approach it using Euler's method with finite differences. Okay, so again, let's just sort of go through here. This is what's in those notes I handed out to you. I approximate each one of these first order derivatives by finite differences and then solve for the delta psi and the delta psi prime, right? And then if I want to step forward, again, I just wrote that system of delta psi and delta psi prime things over here. And again, we're doing what's called Euler's method for a system of first order differential equations. If I want to step forward, I'm going to write delta psi as delta psi prime as psi prime at the next position up minus psi prime at the current position, and same thing for psi, right? When I write those down, these differential equations, the change in psi is just going to be psi prime times delta x. That's easy. All right. And that allows me to solve for what tells me how to step forward. Now, notice I'm not keeping track of just one thing as we go along here. If we have a second order differential equation at each position, not only do I have to keep track of psi, but I need to keep track of psi prime. And you'll see in the code, I'll show you in just a second, that I've just whipped up that I call it PSIP, just for psi prime. And so the assumption is I've defined what psi and psi prime are at some position, right? Second order differential equation, you got to specify both the rate of change and the value there. Okay, so we've got to specify that. And this tells me how to get it at the next x, right? Or I might think of this as psi prime at n plus 1 in terms of psi prime at n, and so on, right? And psi at n. Similarly, I can step backwards. I could also write delta psi over here, or delta psi prime, as psi prime at x minus psi prime at x minus delta x. And that gives me a rule for how to step to the left, or to step to more negative values. And we're going to want that because what we're going to do for this assignment is take a nice symmetric potential, and we're going to start out with some initial values in the middle, and we're actually going to solve for those, time independent Schrodinger solutions moving in both directions. So we're going to start in the middle and move them to both sides simultaneously as we step forward and backward. Okay, that's called Euler's method. And so you could write that, something like that in MATLAB code. There's a slightly better method for differential equations that involve some sort of oscillation. And as we've seen, our solutions to the time-independent Schrodinger equation often have some oscillatory region. So this might be slightly better than Euler's method. If you talked about Euler's method at all in your differential equations class, you probably heard that there's some problems with round-off errors sometimes, and they can really accumulate badly. If you are trying to model something that's orbiting the Earth, right? And it should be going around and having a constant radius, if I set the initial conditions correctly. You overstep at every step forward in time, and it ends up spiraling out, and that causes energy's not conserved. It causes all sorts of problems because you're always overstepping. The Euler-Kromer method really is almost the same thing, except the Euler method, notice it says, if I want to get psi prime and psi at the next position to the left, here's how I do it in terms of the values of psi and psi prime at the current positions and delta x. The change in the Euler-Kromer method is, instead of these things that I've circled here in these two equations, notice at this point, if I compute the new psi prime at the next position over first, I could use that instead of the old one, right? I'm using psi prime at the old position here, but I've already calculated it in what it is at one position to the left and at one position to the right. So I could use those values there instead. That change ends up making so that when something's periodic, when you gain a little bit on one side, you lose a little bit on the other, and on average, you don't overshoot or undershoot, and it keeps your solution a little bit more accurate. You may have heard in differential equations, I don't know if you guys talked about the Runge-Kutta method. That's much better than this for a wide range of differential equations. So we're not going to worry about that, but if you want to program in the Runge-Kutta fourth order method, which is one of those really, really accurate stepping methods for solving differential equations and moving right or moving left, you could do that. I'm just not going to talk about it here. Euler's method is sort of good enough. Euler-Kromer is what I would suggest sticking with here in your MATLAB code. Okay, so in order to generate a solution, we have to specify some initial position, and we're going to choose the very middle position. In fact, in the code, in the code, what I'm going to do is, since I want the middle position to be my starting position, I might call that the end position here. I'm going to imagine I take the same number of steps over here. And I think in my example code, I allow 50 things to the right of the middle position and 50 things to the left, plus the middle position. That makes 101. So my X vector is length 101. That means it definitely has a position right in the middle. And I can just step over and solve and solve and solve. And I loop through 50 times to add those 50 positions on either side. Okay, so we're going to step both to the left and to the right. And again, we're going to consider, at least in this example, I'm just going to look at an even potential, but you don't have to look at an even potential. You can look at an arbitrary shape potential as long as, well, of course, it's got to have some definite minimum, and it has to go up to plus or minus infinity. Although you're welcome to use an even potential, right? We've talked about quadratic potentials. That's the harmonic oscillator. We've talked about the infinite square well, but you could do something like a quartic potential, or this would be, you could write a quartic polynomial that looks like this, so it would be sort of like a double well potential, right? Or some other functional form. You can make up whatever functional form for v of x you want. Okay. In this case, if I choose a symmetric potential, right, same to the left of 0 as it is to the right of 0, then the solutions are either going to be even or odd. And so I would suggest, because it's going to be easier for us, I would suggest, actually, I take back what I just said, you should choose a symmetric potential, because we're going to actually generate the even solutions separately from the odd solutions. And if you don't have a symmetry to your potential, you have to think a little bit more carefully about it. So I want you to use some symmetric potential, and it can't be anti-symmetric. It's got to have a minimum, so it's got to be some left-right symmetric potential. Okay, so the solutions are even or odd. And what we're going to do is generate them with two separate pieces of code. To generate the even solutions, we're going to imagine right in the middle, if I'm generating an even solution, so I'm generating a psi as a function of x here, and if it's even, it should have a derivative of 0 right in the middle. If it's going to be left-right symmetric, right, it can't have a non-zero derivative right in that middle position, because then it wouldn't be an even function. So if I'm generating an even function, generally we're going to assume that at x equals 0, that's going to correspond to this middle position here, right? It's not going to correspond to x in position 1, but rather in whatever the middle index is. We're going to take that value to be 1, the height of the function to be 1. The more important part is that the derivative of it is 0 there. Okay, so we're going to take psi prime to be 0 there and psi to be 1 there. You might say, well, why 1? What if its value is 2? And that's fine. If I took psi at 0 equals 2, I would have gotten the same solution but multiplied by 2. And we know that any multiple of a solution is really the same solution as far as quantum mechanics is concerned. So we're not going to get a normalized solution, but we could, after the fact, normalize it if we wanted. What I'm concerned with here is not the normalization, but rather the shape of the function. So setting this as 1 is good enough. What about the odd solutions? Well, what do you know about odd solutions? Whatever it's doing over here on the right side, it's got to be doing the negative of that over here on the left, which means if you've got an odd function, it's got to go through 0 at the origin. So if I want to generate an odd solution, I'm going to set the value of the function equal to 0 and set the derivative of the function equal to 1. And you might say, well, why 1? What if the derivative is 2? Well, if the derivative is 2 and I get the solution for 1, the solution for 2 would just be multiplied by 2 again. So it's not really that different. It's just stretched out vertically. But other than that, it's the same function. I think in the notes, I don't know if it was a typo or what, but this prime was not in the version of the notes. Just, if you want to pay attention to detail, when I was making these slides and just pasting these versions of the notes in there, that wasn't there. Oh, and I'm sorry, Alvis, you got to tell me to stop screen sharing because I was writing on the board and you weren't seeing it. I'm sorry about that.
Oh, actually, I am capable of seeing it.
Okay, so you're just maximizing. Yes, I forget that you can just click on the window to pin it. Good. Okay, so how are we going to do this in MATLAB? And let me just show you kind of, some quick code. And then what I suggest you do is keep on refining it, making the code do more work. What we're going to do is choose an energy value that's close to the minimum of the potential. That means it should be, we know that already from our discussion in class, that if you've got a potential, you can't have an energy down here below the minimum of the potential. Why? Because it's not going to be normalizable. So that's not going to be one of our bound state solutions. But maybe I choose an energy, right? In my differential equation, I don't have it up there right now, but in my differential equation, there's an E in it. And in order to solve that differential equation by stepping forward and stepping backwards, I've got to decide on an E. And our whole point of this is we want to find the collection of E's, the spectrum, that are allowed, that give normalizable functions. And we want to find the psi's that go with them, the psi for each allowed E. So I'm just going to choose one at random. It's probably not an energy eigenvalue, right? It's probably not going to give a normalizable function. That means the function is probably going to go off to plus or minus infinity as you head off to x equals plus or minus infinity. But let's try it. And let's generate an even solution to the time-independent Schrodinger equation for both forward and backwards values of x. So I'm going to simultaneously step forward and step backward. And let me just show you some MATLAB code here. And, I have no idea. Some of you are much more familiar with MATLAB because you've been using it recently. Some of you maybe not. But some of the housekeeping things that I normally use is if I'm writing a script here. So I start a new script and it opens up the editor. And I always start with clear all, close all, because that means if you have any variables that are defined, close them out so that we don't have any variables defined. If you've got any figure windows open, close those. That's just a nice way to start every script. And I'm opening up a figure window, figure 1. There are some constants that come into my differential equation, right? H bar is in the time-independent Schrodinger equation. I'm going to do a test, and I suggest that you do this test first. Because the harmonic oscillator potential comes out so nicely, right? The allowed energies should be evenly spaced, and you already know what the solutions look like. You know what the psi 1 and psi 2 and psi 0 look like. And the potential energy is, in terms of omega, is 1/2 m omega squared x squared. Is that right? I think that looks right. 1/2 m omega squared x squared. That's like 1/2 kx squared, but written in terms of the resonant frequency omega. Notice I could have put in SI units here, but then my axes ranges would be really funky. When I put in H bar is a tiny number in SI units. So my range of X values is going to be really tiny. And my range of the amplitude of psi might be really tiny too. So instead, I'm just going to set H bar equal to 1 for this. In some units, H bar is 1, right? If I choose the right units, H bar could have the value of 1. Same thing for omega, right? If I choose the right spring constant or whatever associated with this, then the resonant frequency might be 1 in SI units. I'm going to choose the mass of my particle equal to 1, just to simplify things. I'm going to put them all in the differential equation, but that way the axes ranges might be from -3 to 3 instead of -3 times 10 to the -30 to +3 times 10. It just makes things nicer. And we'll still be able to see if the solutions look right. And what I'm going to do is step through a bunch of energy values, right? I'm going to start down near the minimum. Maybe if I suggest that you kind of make the minimum of your potential energy function at 0. That way, you know, you don't have to check any negative E values. They're definitely not going to give bound states. So I can start at 0 and draw a solution, step up bit by bit by bit by bit by bit, and look for ones that look like they're almost normalizable. I probably won't hit an energy right on, but I'm going to look for an energy that looks like it's close to being normalizable, and we'll talk about what that looks like. So I'm setting up a vector of energy values that I'm going to test. I'm saying I'm going to start at a minimum energy of 0. If I'm doing here, I'm doing the harmonic oscillator potential energy. So, you know, this would 9 h bar omega, that's n plus 1/2 h bar omega, that goes above n equals 8. So that's going to give me, you know, the first 8 or so bound states, right? And I'm just going to make a vector that contains all the energies evenly spaced between there. I'm going to draw a function for each one. And most of them are going to go off to infinity. They won't be normalizable. But every once in a while, I'm going to see, we'll be able to see when they're almost normalizable. We'll see that in a second. Okay, I've got to define my X range, and I've got some indications of, you know, you might say, well, why are you choosing this as your maximum X on the X axis? The answer is, well, there's some guidelines on the very last page of those notes that tell you for your potential kind of how to estimate what a good X range would be and what a good range of energies would be so that you'll hit, say, the first 6 bound states for sure. Okay, this number n step in my code is how many steps I'm going to take forward from the middle. So I'm starting right at that middle spot. I'm going to take 50 steps to the right, 50 steps to the left. That's going to give me 101 values, right? Because I got the one that started at plus 50 on either side. So 101 values. That's what I'm calling nx. That's how many x values I have. 2 times n step plus 1. So I'm going to do 50 steps. And in each step, I'm going to step forward and backwards. One more, one more, one more until I fill out the function using those step forward and step backwards kinds of relations. And then I make my x axis vector. And I can immediately calculate dx, which came into my differential equation, right? Okay, and in terms of the x vector, I can also define the potential, 1/2 m omega squared x squared. Now, omega I already defined as 1, and m is 1, so they're not really doing anything in there, but just so I recognize this. But x has different values in it. Whenever you have a vector and you want to square every value, you got to do the dot to the power. Hopefully you guys remember that. Okay, so this is generating what the potential energy is at every x value. So that's giving essentially v as a function of x. And what I'm going to do is loop through all the energies. And before I do that, I better, you know, just at least pre-allocate some space for my solutions, psi, which is going to be of length, same length as the x values, and psi prime. And we're going to fill those in as we go. Okay, so let's go from the first energy until the very last energy. I can't remember what did I make NE max up here? 50. So I'm going to do 50 different energies. Okay. So first, the first energy, that's going to be right down at 0. Let's draw it. In this case, n step, remember, I set at 50, and I've got 101 x locations. So n step plus 1 is 51. That's that middle index. N step plus 1 for my code here is the middle index. And what I'm calling this NPC is like saying, this is the current location I'm at for stepping forward and stepping backwards. P is for plus, that's for me stepping forward, and M is for minus. So this is the number index I'm at for stepping forward, that's plus, that I'm currently at, C. Okay, and they're both going to start out right at the middle index. I'm going to set the current energy equal to the relevant value from the energy vector. And at that location, I could have put this as NPC here and NMC, right? But in any case, at that location, at the very middle, I'm going to set the value equal to 1 and the derivative equal to 0. That means I'm looking for an even solution, right? And then I have to do that step forward and step backward process. So I'm going to say n step is 50. I'm going to take 50 steps forward. And at the same time, I'm going to do 50 steps backwards. Psi prime at the next index for stepping forward is equal to psi prime at the current index for stepping forward plus, the other stuff that's in the differential equation. And similarly, what's the next value of psi according to the system of differential equations? And here I am stepping to the left using the stepping backwards solution. And once I've done that, I'm going to set the index of the current position for stepping forward up by 1 and the index for the stepping backwards solution down by 1. And then I'm going to repeat. So I'm always going to be stepping in both directions and filling out this until I get all of psi and psi prime with 101 values in them. I could do that. I thought this was just a step easier to understand intuitively, right? Just the fact that I have a current index that I'm on for each one, right? And they're just going to be going down by 1 and up by 1 each time. But you could just compute them in terms of n step. Yes. No, I want to start. In other words, I want to start. So this in my code, this is 51 here, and I want to define both psi and psi prime at that initial condition. And then I'm going to use those to step both them forward and backwards and so on. So I want them to both start in the same index. Okay, good question. And then I'm essentially done, right? I'm going to keep repeating that, but I've got this code so that we can visualize it. Each time for each energy, I'm going to pull up a figure and I'm going to plot the potential in red, and I'm going to plot psi in black. And I'm just going to label the axes so that we can see it, right? But if you can't remember how to do that kind of stuff, feel free to ask me or someone else, okay? And we can talk about this psi max stuff in the end. But then I'm going to have the code pause. Pause means wait until I hit a button on my computer, and then you can go keep running. And that way I can sort of step through this so that it won't happen too fast. All right, so let's run this. That's about as bare bones as I can get this. Unfortunately, I can't see it. Here's my run button. Okay. All right, so here is the solution for my lowest energy value. The potential is shown in red there. So that's my quadratic potential. I chose the harmonic oscillator, and I would very strongly suggest you start with the harmonic oscillator because you'll know when your code is running right. You already know what the solutions look like. You know what the energy should be. Here's my solution shown in blue. It's not normalizable because it's going off to infinity in both directions, okay? It's paused now, so I'm going to hit the space bar. You don't have to pause yours. You can have it keep going through, but I just wanted to illustrate. Oops. Okay, I stepped up in energy a little bit. Still divergent, right? Still not normalizable. Let's keep stepping up. Oh, what happened? It was diverging up to plus infinity in both directions. Then I stepped up in energy a little bit, and now it's diverging down to minus infinity in both directions. What do I know? Well, what I know is that between the two energy values, and I'm printing out the energy up here in the title of this graph, between those two energy values, there's an energy eigenvalue. Because those two sides are behaving symmetrically, they somehow went down in one step and went down like that, but they must have passed 0 along the way. And so somewhere, if I delicately zero in on that position, there should be an energy eigenvalue between those two energies that I'm clicking through. Let's keep clicking through. Okay, no energy eigenvalues there. Oh, you see it's starting to turn back on itself. You see how we're getting even solutions? That's because I chose psi equals 1, psi prime equals 0. We'll do the odd solutions in just a second. Still diverging to minus infinity. Whoop, there is an energy eigenvalue between those two energy values. So what that means is I've got a very crude estimate of where some energy eigenvalues are for even functions. And then I can go back and do, 500 fine grain, you know, set my E min to be the lower one of those, the E max to be the higher one of those in 5,000 steps, and hopefully find one that really looks like it's asymptotically going to zero. We'll see what that looks like in just a second. This is a very coarse grain kind of thing. So I keep stepping through. Again, this is just to illustrate to you, but you can see we're passing energy eigenvalues. Every time those arms flip up or down, we've passed an energy eigenvalue. And so I know there's a range of energies that I need to zero in on more precisely. We didn't get a good picture of the graph, but if you get E very close to an eigenvalue, then you'll see it looks like it's asymptotically going to zero. So, okay, so, and again, if I wanted to do the odd solutions, let's go back to the code here. Here it is. This is where I chose it, right? I chose psi initial in the middle to be 1. Let's choose psi initial to be 0 and the initial derivative to be 1. And that's going to give us an odd solution. And when I run it and start going through, we can see odd solutions, right? Anti-symmetric, still diverging to plus or minus infinity on both sides. But at some point, the arms flip. So again, there is a range of E's that I could search more delicately for an energy eigenvalue. And as I just hold this down, we see it sort of developing that way. So that's my initial stab at a code. And I want you to produce something like that so that you can see that you're, you know, as you zoom in on an energy eigenvalue, you may get something that kind of makes sense in terms of the solutions we've already seen. And the energies, we know the energies, the allowed energies for the harmonic oscillator, En is n plus 1 h bar omega. Now in my code, I set this equal to 1 and this equal to 1. So I should get allowed energies in my code of n equals 0 is 1/2, n equals 1 should be 3/2, 5/2, 7/2, and so on when I zero in on them. Okay, so that's the crude sort of getting it going kind of level of code. And now here's a sort of code where I've made everything a little bit automated, but it's the same basic kind of code. I'm not going to go through it with you, but when I run it, I have it in this code, check for even and odd solutions as it steps up in energy, and it does the zeroing in automatically as it goes through, and then it makes the nice plot. So thought I clicked run. Do I need to go over here and kill something? Huh. Okay, well, there it is. It ran there. I hit run a couple of times, but this is the output, which is very similar to the graph you see in Griffiths in the chapter on the harmonic oscillator, or the section on the harmonic oscillator. Ground state, first excited, second excited, third excited, and so on. Notice the energies in my code are 1/2, 3/2, 5/2, and so on, right? So they agree with my setting h bar equal to 1 and omega equal to 1. I didn't quite get it, so it goes down to 0 here, and that's sort of unfortunate for this picture. You know, if I chose my energies to be a little bit more fine-grained, if I go back to the editor and say, I did 500 energies there, let me do 5,000 and see if we get a better picture where at least you're never going to get that energy eigenvalue right, but at least for the range of your picture, it should look like it's going to 0, right? If you don't hit it exactly right, it's eventually going to go off to infinity, but we want it for our picture like this. So what I kind of want you to do is, if you can, produce an image like this for your chosen symmetric potential. Kind of like that image that's in there. So show your potential energy function with a little gray line in the background, show the allowed energies, and use that kind of as the 0 line for each of your psi's associated with those energies, very much like Griffiths has in the harmonic oscillator thing, right? And that's the goal. But I wouldn't try to do this first, right? Try to see if you can get some solutions that make sense for the harmonic oscillator. And then if you want, tweak your harmonic oscillator code so it does something nice like this. And then finally choose a different potential that's still symmetric, left-right symmetric, but is something we haven't seen. and try to make another, somewhat aesthetically pleasing plot. All right, any questions about that?